Thanks. So just to orient you a little bit, this talk is kind of structured as, I guess, a little 101 if you have been working with machine learning or in particular neural network models for other problems other than NLP, and natural language processing problems tend to have very similar characteristics because of the nature of language. And so there's kind of a little template has emerged in the natural language processing community for how to solve these things. And if you sort of understand this sort of basic framework for how these models are put together, it becomes much, much easier to understand, the disparate results that are produced. And models which otherwise sound like, kind of complicated and hard to grasp become much easier. So I see it as a little bit of a key to understanding these things. On the other hand, if you are knee-deep in natural language processing research already, maybe this talk won't have so much new to offer. But on the other hand, maybe seeing it put in these terms will be useful as well. Okay, so getting started. Let's sort of start with an example problem of something that you want to do. And I think a key to understanding machine learning algorithms and problems is often, instead of thinking about things in very mathematical terms and thinking about the equations, taking what I call a computer's eye view of things and imagining that you have the processing capabilities of the model that you're interested in and trying to view the data that way and think about how the data looks from that perspective. So on that note, imagine that you're sort of implementing an algorithm yourself. So you're going to give yourself this task, and you need to come up with a system that's going to solve this. So imagine that you don't speak Indonesian, and you're given a bunch of rated restaurant reviews in this language that you don't speak, and you're given a quiet room, a pencil and paper, a week, and a lot of coffee. So how can you predict the ratings for the new reviews? What could you do here? What sort of system could you come up with? So here's a little view of the data of what this might look like. And so you can see here, all right, you've got a bunch of text. And what I don't want you to do here is, basically import your knowledge of this. So, for instance, you can recognize some of the words here like takeaway, and you don't want a system that goes like, okay, I'll read the things, look for the English words I already know, and use that as the basis, because that's not really the cheating. It's not the computer's eye view. We start off with this assumption that the computer doesn't know that like cozy place is a positive word or something. You have to just treat these as like pretty opaque identifiers. Okay, so what would we do with this? Okay. Well, when we're thinking about this, we have to, keep in mind that we're necessarily going to be throwing away information. So we have to figure out what to generalize. We have to figure out what information matters in the example and what's not. So, for instance, most sentences are unique. So you can't just say, all right, I'll read a sentence, decide whether it's positive or negative and use that, or I'll take, these two large chunks, because then you won't be getting any further forward. So this process of figuring out what to do and how to solve these problems is necessarily a process of figuring out what doesn't matter, like making these simplifying assumptions so that you can try to guide the model towards, how to generalize. Okay. So, all right, what would we do here? What's a sort of basic suggestion? Well, here's how to implement a sort of basic bag of words model. So we can say, all right, we want to know whether the words usually occur in positive reviews or negative reviews. So imagine that we could, just track a positivity score for each Indonesian word, and when you see a new word, assume its positivity is 0.5. And then we're going to count up the average positivity score for the words in the review. So that's how we're going to make our prediction. And then we can, sort of imagine, even as a human, implementing a little perceptron algorithm to actually tune these weights. So, if the total's greater than or equal to 0.5 and the review is positive, we can say, okay, the fit theory worked. Similarly for this. And then if we overestimate the positivity score, we would just, decrement the positivity score that led to that prediction. And similarly, if we underestimated the positivity score, if the total was less than 0.5 but the review is positive, well, we want to increase those scores slightly. And so this is just a perceptron algorithm, right? So it's a bag of words, perceptron algorithm, but you can imagine implementing it yourself, and you can imagine the view of the data that you would be taking as you're stepping through that process. And I think that this is an instructive process in sort of thinking about what's good or bad about different approaches to solving a problem with a machine learning model, like really thinking about the process that the model is stepping through in order to learn these things. So we can also ask, what information are we discarding in this? Like, where are the weaknesses? What are the problems with the process that we're enacting here? The assumptions that we're making here are that different words are unrelated. So we're treating these words as opaque IDs, and if some word, even if it's semantically similar to some other word, if we haven't seen it before, we don't know anything about it. They've got the positivity scores of each of these words are completely independent of each other in our process here. Similarly, we're also assuming that words only have one meaning. There's only one positivity score that we're attaching to each of those, IDs identified by, this string of characters. And so in many languages, this is, super problematic, especially if the writing system isn't vowelized. The words are not very distinct, and we, have a real problem from this type of bag of words process. And finally, we're also assuming that the meanings of these words can be understood in isolation, that the context of them is not so important, and that it's not so important to look for a meaning of a whole sentence that composes these meanings, that, we can basically just look at these words. And so it turns out that for many, many types of problems, these are good generalizations, these are right reductions, these are reductions which help us. And so it's not necessarily problematic if we take a machine learning model and end up with a model that has these sort of characteristics, because often that's this is the kind of efficient way to generalize. But what we'd really like to do is avoid importing these assumptions into the problem to start with. We'd rather not have to guess what generalizations to make. We'd rather not have to guess what the relevant reductions are. And so what we'd really like to do is have a machine learning architecture that's able to basically learn which pieces of information to throw away and learn these internal representations. And that's where I think the neural networks are particularly strong. Okay, so here's how we are going to do that. There's going to be these 4 little steps that we do in transforming our representation from these word IDs towards something that we can actually predict on. Okay, and there's 4 steps: these embed, encode, attend, and predict. Okay, so in order to basically orient you in this, we want to be thinking of data shapes and not application details. So we don't want to be thinking too much about the fact that we're trying to solve a sentiment analysis thing of assigning scores to reviews, or versus trying to find spam, or versus trying to identify authors or something like that. All of these things have the same input data and same output shape. And so we want to be solving it on sort of that level of generalization rather than thinking too carefully about the application or vertical that we're in. And so once we're doing that, there's really actually only a few relevant data shapes, and so we only have a few transformations to make, which is why we only have these 4 steps. So we have one of the sort of relevant data types that we want to be processing is like an integer or a category label or some sort of discrete ID. Another one is a vector for a single meaning, and then this is sort of another very important level of representation that's a little bit less obvious, but that's having sort of a matrix representation or a sequence of vectors where we've sort of calculated these vectors independently of each other. So this is something like the representation of a sentence that you get after you've separately embedded each of the words, but you haven't yet done anything with the context of them. And then finally, this matrix is when you've actually sort of calculated this row of meanings based on the fact that it occurs before this row and before this row. So these are the kind of data shapes, and then I'll show you how the different stages are basically just these transforms between them. So first of all, the embed step is really designed to solve this problem that all words look unique to the computer. So, if you're taking a computer's eye view of these things, dog and puppy are just these strings of letters. And so it's easy to learn that, what's the probability of this ID given dog. But actually, I don't quite. So, basically imagine that, why did that go forward? Yeah, so imagine that, during training you had seen this word dog, and okay, what's the category of that? But then you might have some phrase which you haven't seen in your training data before. So what's the implications of that? Like, what does this mean? Like, how do we get this relationship between those two words which are otherwise similar, and not have to learn those as completely separate representations? So the solution here that has basically come up over the last 5 years, and seemed like a pretty satisfying solution, is learning these dense embeddings, and this has been working super well. So this, the basic insight here is that, this distributional hypothesis, you should know a word by the company it keeps. And this is just that, if you have a word like dog, you can just look at the fact that it occurs after words like bark and after words like this, so it's a noun. And you take all of these contexts that you've seen the word in, and you use these to calculate a meaning representation. And so this doesn't, require a very formalized process of organizing words into some tree of categories or organizing a thesaurus or something manually, and we can get this type of thing just off unlabeled data, and it tends to be a pretty effective process. So the second problem, after the embed step is that we're discarding context. So you can imagine these two reviews. I don't even like seafood, but the scallops or something else is a very positive sentence, and then you should go somewhere else, literally anywhere else. Now, the key here is that if you think about what word sort of triggers the negative sentiment in the second one, and which word triggers the positive sentiment in the first one, you really can't identify anything. The meaning is really built over the whole construction, and that's going to be a problem for this sort of bag of words approach. So we need some way of learning larger phrases, and we can't even assume that those larger phrase meanings that we're learning are going to be from a sort of fixed inventory. It's not even satisfying to say, all right, I just want to find the special words with spaces, which are just things like an entity or something where it's still one lexical entry. Instead, we do want some sort of way of calculating meaning representation for a larger unit like a sentence. So what we're going to do here is this encode step, and this is where these BILSTM models or convolutional neural networks are used in natural language processing. And so this has been a super important development in natural language processing over the last few years. And I think that this is getting us over that bag of words representation has really been one of the drivers behind generalizing natural language processing to other problems and basically getting better results. So here, what we're going to do here is we're going to take this list of word vectors, and we still want one vector representation for each word in the sentence. But instead of having those be just completely independent of each other, instead of basically always looking up the same vector for dog, regardless of what words are around it, we want to modify that vector after we've learned it. And so this is this encode step, and that there are lots of technologies for this. So more recently, people are using attention layers with self-attention to carry out this step. But when you're seeing these results and thinking about them, it's useful to keep in mind, okay, that's just another way of solving that problem. And you can basically say, okay, I'll, use this instead of that at that stage of the process. So, it's nice to see the abstraction behind this and think of it in terms of this data transformation step. So finally, step 3, all right, what's this, if we have this representation of a whole sentence, and we've got one row for each word in the sentence, even if those rows are kind of context sensitive, we still have kind of too much information. We've got this matrix representation, and we really want a summary of all of the information in that sentence. So how can we make this sort of context-aware summary? And so this is the encode step, and so attend step. So this one's a little bit vaguer than the others because there's a few different ways that people are doing this. But the basic principle of it is you can have some sort of vector that represents a query or some sort of vector that represents, a thing to pay attention to. And that might be calculated in translation from the opposite sentence, or even you can have a matrix that you're attending to. Or if in text classification, people have found using the query vector as just a free parameter is also something that has worked well. And so basically this is just sort of a weighted summation. So you basically often people take a transformation of this matrix with just an affine layer, and then you then reweight it according to its similarity with the query, and then you can basically just take a sum of this. And so this is this sort of learned way of getting a summary. It's only it's not worlds better than just taking an unweighted summary, but it is a nice improvement that often reduces errors by 10 or 15%. But I would say that of the different stages, it's usually more important to basically have some sort of encode step, like something like a BILSTM, then the attention step usually has a slightly lower impact. But it's still, definitely a good improvement. Okay, and then finally, usually we don't actually want to deal in a sort of continuous domain. Usually applications want some sort of ID that's discrete that can be fed forward into an application. So, if we want if we're doing, say, text classification, it's often, only an intermediate step to come up with a vector representation of the sentence. That's nice and all, but what we're really trying to do is sort it into a bucket. Like, for instance, figure out a review score, or figure out what labels to classify it with, or that sort of thing. So, given this vector, we then want to make a prediction. Fortunately, the lessons around this are very similar to anywhere else. So really, you just use a multi-layer perceptron here. So it's something like a feed-forward network with rectified linear units or something. So yeah, we can see what this is like. Well, we're just taking this vector representation, feeding it usually through a network, but actually you can use other machine learning layers on this as well. And we want to get a specific ID out. Okay, so now I'll just take you through otherwise complicated looking networks that you can sort of understand in these, in terms of these pieces, and you can see that they're actually kind of simple. So this neural network's a hierarchical approach for classifying text. So what we're going to do here is imagine that these two things are different sentences. So sentence 1 and sentence 2 of, say, a 2-sentence review. And we're going to take our IDs. So sentence 1, imagine that this consists of 3 words, and this also happens to consist of 3 words. And so we take these IDs and we separately embed them into some vector representation. And so at this point we have a representation where no matter what, every instance of some word is going to have the same vector representation at this point, regardless of its context. But we do have these a vector representation after the embedding layer. Then we're going to separately feed each sentence through, say, a BILSTM network. So this will read the sentences in turn and try to output a modified representation of them. And so it's just going to learn some way of what that word means in context. Then finally, we might take an attention layer. And so here we would, in the case of this paper, they basically just learn the attention weights as a free parameter of the model. And so here we get just a weighted summary of the words in the sentence given the other words in the sentence. And then finally, we can then take the 2 sentences as another sequence of vectors. So we've got the same sort of representation here as we did here. And then we can run another BILSTM over the sentences so that we are able to read the sentences in context. And then finally take an attention layer, and then finally get a prediction. So you can see here that we've got the same process running over the sentences as we had over the words. So it's a hierarchical model that's able to build up a representation of a whole document out of the representation of individual words passing through these different layers. And so this actually works super well. Even though it feels like there's all these steps and moving pieces, actually it is kind of simple, and it can be implemented without so much code. So I find this quite satisfying. And the thing to understand here is that it's unlikely that the model will actually learn really important dependencies between the sentences. Like, the fact is, if you're classifying reviews, usually it doesn't matter that much that a bag of sentences model is probably actually going to be pretty good. So we shouldn't be too upset if the reductions that the model learns out of this complicated model, if these inter-sentence orderings don't matter that much. I don't see that as like sort of invalidating the technique. Rather, the way that I think about it is that it's sort of no worse to do this, and it saves us from having to assume what's important ahead of time. And so this is this process that I mentioned before about learning what to learn. And so even if it turns out that we could have done about as well from embedding the words and then making a prediction based on that, and these other layers didn't add that much accuracy, well, it may be inconvenient to have a slower model, and if we care about processing speed, then we can basically run that evaluation. But it's very nice to have a default model that is able to take into account all of these things in theory if it were necessary. And so I think that it's like we're really gaining from generality of developing a code base that can work across problems, even if the problems can turn out to need other features, because it can basically select what's important and what's not. So now here's another example of this with a slightly different input and output shape. So in this case, instead of having two sentences as to two things on either side in a single document, what we'll be learning here is a relationship between two separate documents. So here in this case, this is a document and this is a document. And what we're trying to learn here is some label that might hold between them. So for instance, does this text imply this other text or does it contradict it? Or if I see this page as a citation of this other page, does that page actually support the argument in that in the first thing that it was linked from, or is it sort of a spurious citation? So this kind of textual relationship thing is something that was otherwise quite difficult to do before we had these dense representations. And the models for this are still not that awesome, but it opens up a really wide range of other applications as we can improve on this. And I do think that this type of model is improving quickly. So again, the model is actually very similar to the other one if you're thinking about it in these terms. So again, we're going to separately embed these IDs and separately embed the IDs for the other text. And we're going to use the same model weights for each of these sides. So it's this what people call a Siamese architecture, which I think is a slightly fancy name for something that's pretty simple. You're just going to run the same model over the two pairs of text. Then we'll again run something like an LSTM or a CNN or something to get this type of words in context representation. Then we run an attention layer that actually compares the two things. So each one of them will be the query vector of the other, and we'll come up with two vectors, one for each of the things, and then sort of concatenate them so that we have a single vector representation for the pair of texts that's able to take into account the words in context and able to it's basically read the two words and read the two texts and compared them. And then finally, we predict from that attention, from that attended vector that we've produced, what the output should be. And then we can backpropagate through to all of the layers when we have an error. So you see here that, again, the pieces are all the same and you've kind of arranged them differently. And if you read a paper with this, it sounds all complicated and confusing. But the underlying things are actually kind of easy. I think it's a good framework for understanding these things so that you can basically have that sort of cognitive shortcut of looking for these common pieces. Okay, so generalizing this a bit or sort of putting this into practice, what if we don't have so many reviews? Like what will we do to, 1 minute? Okay, I think I've only got a couple of slides, 1 or 2 slides left. If we're putting this into practice, what we really care about is learning these representations in a sort of more generalizable way. So we want to do something like transfer learning. Here again, I think it's useful to keep in mind the different layers of this. And in particular, the word embeddings are super easy to learn generally because if you've only got one meaning for a word out of context, then it seems fairly obvious that you don't necessarily need to learn that over your specific data. You can maybe make sure that you're learning representations for specific words of your domain, but most of English is kind of common between these things. But you do probably want to have something like a context vector or be able to pre-train a language model or something so that you can also customize the embed step and then really only be learning the attend and predict layers on the much smaller training data that you have. To sum up, the points here is the neural network models let us learn what to learn. And it's almost always the case that you could construct an alternate model that basically didn't it didn't necessarily use all of these features and didn't work in the same way. So for instance, you can probably construct a linear model that is able to extract features that get you similar accuracy to the neural network. It's just that takes more time and specific effort, whereas the neural network gives us a much more general approach that it means that we don't have to do that sort of more problem-specific work, and we don't have to do as much problem-specific reasoning and experimentation. Of course, the knowledge that we're injecting here, the knowledge that we are learning, has to come from somewhere. It's good if a bulk of that can come from unlabeled text, but then and then we can have a small number of labels that are much more specific to the problem and really speak to the specifics of the application. So we want to learn the general facts about the language from unstructured data and learn the problem-specific parts from a small labeled corpus that's specific to the problem. And so, I think that the general template for this is pretty well understood and has been stable over the last couple of years. And now the innovation is really on, kind of fine-tuning each of those components and, basically improving the efficiency of them. So, thanks.
Something different?
So the question is, how does Spatie currently do text classification? So the default solution that we have implemented in Spatie is very biased towards what I hope would work well in our annotation tool, Prodigy, and so in particular what works well for active learning in Prodigy. So it does use a convolutional neural network like this, and it also is, there's an ensemble of a convolutional neural network and a bag of words text classifier. And the reason for that is that the bag of words model tends to learn much quicker. And so if you're sort of starting from scratch in a new annotation project, the active learning is much more effective that way. And so this is the default model that's there. There are many text classification problems where you'll get much more efficient processing if you use something like Valpil-Wabbit, which is a very well-tuned library for text classification with bag of words models. And so I'm always telling people that, if they have a problem that looks like that, and in particular if the documents are not so short, that they ought to try this out. And so to avoid repeating work, we implemented a solution also that works well on problems which these bag of words models don't tend to perform well at. And in particular for short texts, I would say that the convolutional neural networks, which are similar to this architecture, work well.